Hello everyone! Today we're going to talk about section 2.3 where we're going to learn more techniques for finding limits. Last time in 2.2 we talked about how to find limits graphically. Later we're going to do a little bit more algebraic. But first what we have to do is we have to talk about what we call the limit laws. These are the things that we're allowed to do with limits, and they're actually very straightforward. And because a lot of it is just a lot of writing and listing, I would actually suggest maybe just printing out this whole page and having it there, maybe highlighting and underlining things, because it's just a lot of writing down. So if you want to print out these notes first and make notes on it, it might make your writing a little bit easier and your hands not quite as tired. All right, so here we go, friends. Let me start first of all by saying, what if I say, given the limit of the function f, as I approach the letter a, from the left and the right, is equal to the letter L. Cool. So the limit of this function as I approach a from both sides is some y value, some number L. And vice versa, the limit of a different function, how about g of x? As I approach the same letter a, whatever number that is, from the left and the right, would be the y value m. All right, that's just the given. So I have two limits of two functions here. The first limit law says the limit of a sum, meaning the limit of the sum of two functions is the same thing as, well, just the sum of the two limits. It's kind of neat to see that in terms of the English switching around the words. The limit of a sum is the same thing as the sum of the limits. So if you're asked for the limit of two functions being added together, all you have to do is take the limit of each one and then just add them together. And we know that the limit of f of x as x approaches a is L, and the limit of g of x as we approach a is m. So the answer would just be L plus m. It's the limit of each one added together. The limit of a sum is the sum of the limits. Limit number 2. Okay, watch the words here. The limit of a difference is equal to the difference of the limits. So same reason. Just not addition, now it's subtraction. You want to find the limit of two functions being subtracted, just find the limit of each one and subtract them. If the limit of f was m, limit of g was m, the answer would be L minus m. Getting the hang of it? They're all going to look like this here, friends. Number 3, the limit of a constant times a function. There's your constant c that's multiplying a function. Well, according to the limit laws, what we can do is we can actually take that constant and pull it out, find the limit first, and then multiply by the constant at the end. If the limit of f of x was L, then this would just turn into CL. So in words, it says the limit of a constant times a function is just the constant times the limit of the function. Rule number 4. Okay, watch the words here. The limit of a product of f times g, you can probably imagine what's going to happen, is take each limit and multiply them together. Is the product of the two limits. L here, m here, so Lm. And just like in multiplication, we could do it with division. So the limit of a quotient, as you see here, the limit of two functions being divided, well, you can just take the limit of each function and divide your answers. So L divided by m, but just be careful because we're doing division. The denominator can never equal 0, so m can't equal 0. All right, last two here. The limit of a power. So if I'm taking the limit of a function raised to a power, just like we did with the constant, it's kind of legal to take that power and just put it outside the limit. Find the limit first and raise your answer to the power. So the limit of a function raised to a power is the same thing as the entire limit of the function raised to a power. If the limit of the function was L, then this would be L raised to the n. And finally here, friends, the limit of a root, same thing. So the reverse of exponent is the radical. If I have the limit of a function underneath the radical, I can take that radical and put it outside. Find the limit of the function first, and then take the radical of your answer. If the limit was L, this would be the nth root of L. Okay. Very exciting limit laws, I'm sure. Hold your applause. But let's actually see this and see how fun it is to play with these. You ready? All right, here's your picture here. Notice the two functions. I've got the f function here, which is in red, and I've got the g function in blue. Take a minute just to look at those. Notice the holes in the graph. That's interesting. Okay, now let's see which one they're asking for. And when they ask them for, let's see if we can use our limit laws to figure it out. Part A says, can you find for me the limit as x approaches 0, from the left and the right, of course, of a sum? And now, as you know, the limit law says that means you could take the limit of one function, the limit of the other function, and then add them together. So why don't we do that? Let's find the limit of each function as we approach 0 from the left and the right, and we'll add our answers together. Okay, let's look at f of x first. As I look at f of x, as I'm approaching 0, 0 is right here in the middle, friends. As I approach from the left and from the right. As I approach from the left, I get 2. As I approach from the right, my y value is 2. They're equal, so therefore the overall limit of f of x is 2. Let's do the same thing with g of x here, friends. As I approach 0 from the left and right on the blue function, from the left and from the right approaching 0, both sides I get 0. So the limit overall is 0. Okay, final step. What is 2 plus 0? Is 2. Final answer for A is 2. So notice how we use the limit laws to break it apart, find each individual limit, and then do the final operation at the end. Okay, I'm going to scroll down just a little bit. Can you go ahead and pause the video and try each of these? They're a lot easier than you think here, friends. Some of them might be undefined or does not exist, so we're going to have to figure out what to do with those. But go ahead, take a little pause, and try the other 7 on your own. Good luck. Part B. Welcome back. Here we go. I'm finding the limit of 2 functions being subtracted. So limit law says let's find the limit of each one, and then we'll subtract our answers. Okay, now we're approaching 2, but again, we're approaching from both sides. So make sure we're always checking the left and the right. Okay, this is as I'm approaching 2. Here's 2 here. So let's try f of x as I approach 2 from the left. I'm getting really, really close to. I know there's a hole there, and that's okay, but I'm getting really, really close to the y value of 6. As I approach from the right side, I got a little bit here. Right side of 2, I get really, really, really close to, again, 6. So even though the point doesn't exist, the limit is still 6 from both sides. Okay, let's do the same thing on the blue graph of g of x. As I approach 2 from both sides, and we go from the left. Again, I know the point doesn't exist, but the y value I'm getting really close to is negative 2. From the right, I'm getting really, really close to the y value of negative 2. So my limit would be negative 2. 6 minus a negative 2, final answer is 8. Part B, or part C here. Okay, now by limit law, I'm going to take the limit of this one, and the limit of this one I'll subtract. But notice I've got a constant here. So what I can really do is find the limit of, as x approaches 2, of f of x, minus the limit of g of x as x approaches 2, and then multiply my answer here by 2, using again the constant inside a function. You can rip out the constant and multiply the limit by the constant. Okay, let's find each one, guys. So the limit is the function as I approach 2. I already did that in part B, that was 6. And the limit over here of g of x as I approach 2, again I already did that, that was negative 2. So here I get 6 times negative 2, and negative 2 is positive 4. So final answer for part C is 10. Notice how we use the constant again and just rip that outside. All right, part D. This is the limit of a product. So we said by limit laws, we can take the limit of each one and then multiply our 2 answers together. Okay, now I'm approaching negative 1. Let's find each one. As I approach negative 1 over here, let's do our f of x graph from the left. As I approach negative 1, I'm getting really, really close to 0. And from the right, again, I'm getting really, really close to 0. So the limit as I approach negative 1 from f of x from the left and right is 0. Now, I don't really have to go on because really 0 times anything is 0. But let's just, for good practice, do it anyway. All right, as I approach g of x, I'm approaching negative 1 right here. really close to what y value? It looks like maybe -1. And as I approach from this side, my y value is getting really close to -1. So again, yeah, the limit from g of x for x approaches -1 from the left and right should be -1. 0 times -1 is 0. Easy peasy. Part E. Now we've got a limit of a quotient, which means I can take the limit of each one, and just divide them when we're done. All right, now we're approaching 0 here, friends. Let's see. As I approach 0 from left to right, I'm not going to make too many markings on the graph. I'm going to see if you can see it now without me writing it down. The limit of f of x as I approach 0, well, actually we did that on part A, didn't we? So f of x was 2. G of x as I approached 0 from left and right is 0. Interesting. We can't divide by 0, right? So this does not exist, or we can say undefined. Numbers look good, but we can't divide by 0. Okay. Part F. Same idea, but we're approaching a different number now. So let's take the limit as I approach -1. F of x we found out was 0. G of x we knew from part D was -1. And 0 divided by -1, that's 0. That one's good to go. Last two. All right. We've got an exponent on the outside, a power. We found out that we can first just find the limit of the whole thing first, and then raise the power at the end. So limit f of x as I approach 0. That's my red graph. When I approach 0, it was 2. And now we can put the power outside. 2 is 4. Last one. Good example of the last log law. We use the radical so we can find the limit of the whole thing and then do the radical at the end. Inside is a sum. So really what we can do is we can find the limit of each one, add them, and then square root them when we're done. Okay, as I'm approaching 2 from both sides, can we use our answers from part B or just again do it again? The limit as I approach 2 of f of x is 6. For g of x, it was -2. Okay, let's do the sum first, and we get 6 minus 2, and then the square root on the outside. Square root of 4, final answer is 2. Great, and that's how we can really use the log laws. So you can see they're really not that difficult. It just seems really daunting when you see all of these written on here, but they're just telling us what we are allowed to do. I'm going to take you guys back, way back, when we talked about these diagrams. When are limits okay? When can we just plug in the x value and get the limit back out? And if you remember this one here, the first one, this one was really good because as you see, the limit as I approach a from the left and the right is the same number, and it's L. It's the y value of L, so that was good. And if you plug in, the point is actually there, so f of a is also L. So that's great. That'd be a great example of plugging in the a value or x value into your function, and whatever answer you get out, man, that's your limit. You're done. But then we had these weird ones, right? So here's this one here. As you notice, as I approach from the left and the right, the limit actually still does exist. The limit is L, even though it's an open circle. The limit as I get really close to A from the left and right side is still L. But do you notice that because it's an open circle, that point is not there. It's over here. So the y value of that is not the same as L. So we wouldn't be able to plug it in. If we try to plug it in, we'd get a different number than the actual limit. And then the last one here on the bottom was sort of like the second one, but there's just no extra point here. Again, you see the limit does exist. It is L as I go from left and right. But the point is not even defined. There's no point at all. It's just an open circle. So even though the limit exists, the point does not even exist, so I can't plug that in either. So the top one is really the best, because if you can plug it in, we'd be good. Like literally, you could do this. To find the limit of a function as x approaches a, oh my gosh, just plug it in. Yay! You get a number out and you're good to go. That's really nice. But as you notice, it's only if you have this magic word here. If your function is continuous. If there's any kind of discontinuity, like holes, removables, any jump discontinuity, or if we're approaching infinity and we're doing jumps, then you can't plug it in. It's only if your graph is continuous. That's when we're allowed to do it. So when are these problems going to pop up? Well, algebraically, we just got to make sure we're not dividing by 0 or not taking an even root of a negative number, because that's what's going to make some of these holes or jumps. So let's try 1, 2, and 3. And first step in a limit, always, if you can just plug in x or the a value, if you can do that, do it. First step, always. All right, let's see if it works. If it doesn't work, we need to find other ways. And we've got them, but for now, this is always step number 1, if you can. All right, number 1. All right, this is a nice graph. How about the limit as I approach 3 from both sides of x squared minus 7? Like I said, if you can just directly substitute 3 in for x and get a number and nothing illegal, you're good to go. Well, let's plug it in. If I plug in 3 for x, I get 3 squared minus 7. This is looking pretty good. How about 9 minus 7 is 2? Well, that's great. We get a number out, and I tell you right now, that actually is the limit if we looked at the graph. So direct substitution worked beautifully, and there were no problems. Number 2. All right, let's see. Can we plug in 2 in for x? Let's see what we get. On top, we would get 2 squared plus 1. On bottom, we get 2 squared minus 1. All right, 2 squared, we got 4 plus 1. On the bottom, 4 minus 1. This is 5 over 3. No problems. No problems at all. I'm telling you, folks, the limit of this function as I approach 2 is 5/3. I guarantee it. Final one. Number 3. Ooh, I see trig. Oh, boy. All right, hold your breath. Ready? Let's plug it in. Got here and we got here. Let's see what happens. If I plug in pi of x cosine x, that means I get pi, which is x, times the cosine of pi. Okay, that's pi times, you remember your unit circle, cosine of pi is -1, cosine of 180. So -1 times pi is negative pi. Again, no problems. These functions were great. They were continuous, and you can just literally plug them in and get that in. So, just to recap, if you're finding a limit, the first big step is just try to plug it in if you can. Now, but if you try to plug it in and you get a problem, what are you going to do? Let's take this one for example. Can we find the limit of x minus 2 over x squared minus 4 as I approach 2? First step, always plug it in. Let's see what happens. I get 2 minus 2. At the bottom I get 2 squared minus 4. On top I get 0. That's not bad. 0 on top is legal, right? That's fine. But look on the bottom. Uh-oh, I'm not liking this, folks. Ooh, oh no. What are we going to do? What are we going to do? So we can't figure this one out this way by direct substitution. Well, what if, without giving you really the answer, what if I just said use a little bit of algebra magic? What could you do to that? And you see some hints here. My eyes go directly to the denominator. Do you see that? And my eyes think, yeah, I could factor that, baby. So think about factoring and canceling, any kind of simplifying. Just do some algebra magic and simplify it. Watch, let's do it. Ready? Come here, buddy. Let's do x minus 2 over, remember factor, this is the difference of squares. X minus 2, x plus 2. And we still got the limit here. Let's not forget our limit. Ah, now that I factored, look what I can do. I can cancel the similar factors. Get out. Poof, and get out. Now that I did that, we have the limit. As x approaches 2, what was left on top? After I destroyed that whole numerator, I have 1. And then bottom x plus 2. Okay, now, why did I do this? Now can I try direct substitution? Now can I plug in 2? Let's see what I get. I would get 1 over 2 plus 2. Well, look at that. Now that works. And it works because this friend here, this function, is equivalent to this function here. They are the same just by simplifying it against some algebra magic. So if you guys try to plug in and it don't work, think about doing some kind of algebra magic. I would put that down as like step 2. Step 1, plug it in, see if it works. Step 2, if it don't, try a little bit of algebra magic. All right, why don't you pause the video and can you try problems 1, 2, and 3 on your own? Good luck. All right, welcome back. Here's number 1. First step always, don't factor yet. I know sometimes you see that I see, ooh, I can factor this difference of squares, but maybe sometimes you don't have to. I'm glad you see that, but always, always try to plug in first. So if I plug in -1 first, I get 0 over 0, and that's bad. Okay, so we can't plug in. So step 1 doesn't work. So therefore step 2 is, let's try to do some algebra magic. Top is fine, bottom is difference of squares. Good. And things cancel. And that changes to the limit as x approaches -1 of my new function, 1 over x minus 1. Now, can I plug in -1? Yes, I think so. Let's see what we get. 1 over -1 minus another 1 is -2, or -1/2. That's the limit for number 1. You tried to plug it in, didn't work, so do a little bit of algebra practice, algebra magic, and it works great. Number 2. Okay, let's try to plug in 0. Ooh, trig again. Oh boy. Let's try to plug in 0 in each one. We get the secant of 0 over the cosecant of 0. Okay, secant of 0. Secant is 1 over cosine. So that's the same thing as 1 over cosine of 0. Cosecant is 1 over sine. So how about 1 over sine of 0? That's looking okay, because I know the cosine of 0 is 1. So the numerator in general, that looks good. But I know the sine of 0 is 0. So right now, this has a 0 in the denominator. That makes me nervous. So plugging in with direct substitution does not work. Okay, there's no factoring here because these are not polynomials. But can we use a little bit of just trig knowledge, because these are reciprocal trig functions? Let me actually take this idea that I started doing here. Here we go. Come over here. Secant is 1 over cosine of x, right? Cosecant is 1 over sine of x. Well, let's do a little bit of algebra here, folks. Dividing by a fraction is the same thing as multiplying by the recip. So I'll keep the top. I'm going to multiply by the bottom, but the reciprocal of the bottom. How about sine over 1? That turns into sine of x over cosine of x. Or, that's the same thing, remember, as the tan of x. All right, let's start over here, friends. How about this whole thing turns into, what's the limit as x approaches 0 of the tan of x? Now, can you plug in direct substitution? I think so. This would be the tan of 0, which is legal, and you get 0. Okay, so not a factoring, not a canceling per se, but again, just using a little bit of algebra knowledge. Okay, how about number 3? Does this look familiar here, my friends? This is our old enemy, the difference quotient here. F of x plus h minus f of x over h. He's going to be really important in another week or so, and you'll see how important he will be. Okay, let's find the limit of that, given that f is this function here. All right, it is a limit, so again, let's plug in h for 0 everywhere we see it. Ooh, well, right there, that was bad. If I plug in h equals 0 there, I get 0 in the denominator, so we are not happy about that. So again, not really algebra with factoring and canceling. It's not trig, but we're going to use this knowledge right here, friends. And let's do the difference quotient like we did last year in pre-calc. All right, so I'm going to apply the difference quotient here on f of x equals x squared. So I'm just going to take this little piece here and bring him down here. Ready? Here we go. F of x plus h would be x plus h squared. That's if I plug x plus h into my function. Cool. And then minus f of x, which is just the function here, all over h. And now, let me see if I can FOIL out that first parentheses. That would be x plus h times x plus h, right? We can't distribute that power, not legal. That would be x squared plus xh and another xh, that's 2 xh's, plus h squared. And then we're subtracting the x squared after that, divided by h. Just like when we did these difference quotient problems, we're going to see some canceling. X squares, get out, gone. We're left with 2xh plus h squared. A lot of these problems you know you're doing right when you have an h in all the terms in the numerator, because now we can factor out that h. You're left with 2x plus h over h. Now we can cancel out those h's, get. And our finally simplified version is 2x plus h. So now I'm going to go back, and now we started with this whole limit of h approaching 0. That's what we started with, but we got 0 in the denominator. But now I did some magic. So now, can I plug 0 in for h here? Yes, I can. No problem. 0 for h goes away, and my final answer is 2x. That was a good one. All right, so direct substitution is a wonderful tool. If you can find a limit with direct substitution, great. If you can't, just need to do a little bit of algebra. Let me show you another tough one. I want to find a limit of this function here. And you can see why this one is so evil. You've got that square root on top, right? But the instructions give you a little bit of a clue. Do you remember in your algebra days, way back when, we would rationalize denominators. But here you're actually going to be rationalizing the numerator. Why? Let's find out. Again, step one, plug it in. Can you plug t in there? And on top you're going to get 0. On the bottom you're going to get 0. So no, I can't plug in the value. Can we factor, cancel? No, we can't do that. So we're going to do step 3. Can you rationalize? And remember, rationalize, you're going to multiply by the conjugate. But here the conjugate, we're going to look at the top for that. We're going to take the first term, the last term, and we're going to put a plus in between. That's our conjugate. So we're going to multiply by t squared plus 9 plus 3. Remember, with conjugate, you do the exact same on the bottom, so you're not really changing anything. Plus 3. Okay. We used to do this all the time when we did the denominators. We've never did a numerator before. Welcome to calculus. Now, look at the top. In order to multiply this out, you got 2 terms and 2 terms, so you're going to have to FOIL it. But you're going to see some beautiful canceling going on. Let's see what we get. On the top, I've got t squared plus 9 root times itself. The root dies, and I'm left with t squared plus 9. Now, when I do a FOIL up here, I got my first. When I do my outers and my inners, you're going to see that they're going to both cancel each other out. You're going to have minus 3 times the root, and over here you're going to have plus 3 of the root. So they're going to cancel. So we don't actually have to do the outers or the inners. We're good to go. Let's just go right to the lasts, which would be negative 3 times a positive 3 minus 9. Now on the bottom, it's really tempting to distribute this t squared into the conjugate part here in the denominator, but please don't. Please don't ever distribute in. You're going to see why in a second, why that'd be really, really messy. Okay, on top we get t squared plus 9 minus 9 all over. Again, don't distribute. All right, you see the 9's on top going away? Once you have that, you're going to be left with the t squared on top and a t squared on bottom that will also cancel. That's pretty. Okay, let's get those out. Poof. You're left with 1 over the square root of t squared plus 9 plus 3. You notice that these t squares were really pretty to cancel because you did not distribute them into the parentheses. If you did, it would be really hard to see them canceling, and you have to refactor them out GCF style. So it's really good that you did not distribute. It made the canceling very easy. But now we have to go back. Remember, this whole thing was all about a limit as t approaches 0, and we couldn't plug in 0 in the beginning because that was bad. Now can you plug it in? Back to step 1. Let's see what we get. I get 1 over 0 for t, right? This is the square root of 0 plus 9, 0 squared plus 9, in fact, plus 3. That's 1 over the square root of 9 plus 3, which is 1 over 3 plus 3. Wow, after all that, folks, the limit of that. Direct substitution did not work. We had to rationalize. It was not pretty, but we definitely got the answer of 1 over 6. And we can check that on the graph too. Good. Why don't you try this one on your own? Pause the video and see how you do, folks. Good luck. All right. In order to go on, let me erase my work. You still have yours down in your notes, hopefully. But in order to make some room, let me erase my previous step. All right. So, like always, let's see if we can distribute the 1 in, or plug the 1 in. You can see right here, right away, we can't. So we're going to have to rationalize. So we're going to multiply by the square root of x plus 3 plus 2, x plus 3 plus 2. Okay, rationalize the numerator. Okay, really quickly, when we FOIL everything, we should get x plus 3, skip the outers and inners, and the last is minus 4. Remember, don't distribute this into the right-hand side. And you'll see here, x plus 3 minus 4 is x minus 1 over x minus 1. You see how that's going to cancel? It's gone. It's gone. I think I'm going to have to finish solving this one, and we're almost done in the next video. Good job, folks. I'll see you soon in the next video.